All right, this section is going to be our last section for Unit 7. So just make sure that with this section, just make sure that you get down a lot of this information just because there's some information to get here, but it's not too complicated. It builds off of what we've done previously. It just kind of expands a little more, and we're going to look at some different terminology. So the first thing is we're going to look at this little e here, which you may have seen it sometime before, like on your calculator or something. But we're going to look at how this can change or fit into what we know about logarithms. So that little e is an irrational number. So you just need to write that's an irrational number. You could just say r number. So it's in an irrational number with a value of approximately 2.7, let's see, 1828, and then it keeps going. But like I said, it's on your calculator. So it's often used for the base of an exponential or logarithmic function, and it's typically used like in real world scenarios. And a good thing about this that'll make life easy on us when we look at these is that when our logarithm has a base, or when our exponent has a base, we call that a natural base. So when it has this base, you can just say NAT if you want. We call that a natural base. And the example of that would just be f of x is equal to e to the x power, because that e right there is our base. So this is the good part. So when our logarithm has that base e, then we have a natural logarithm. Okay. So a natural logarithm, so we'll just say natural log. A natural logarithm is good because we can abbreviate it, and you've probably seen this on your calculator too, but I'll give you an example of what that would look like. So that would be f of x. Let me get rid of this because I wrote it too big. So if we had f of x is equal to log base e of x, which we can just call that e. I'm cool with that. If you have a logarithm with a base of e, that's actually a natural log, like we just said, and we can abbreviate that to f of x is equal to ln of x, which some people call that ln, but I'll probably just say natural log of x. So that is what's cool about this. And if you look on your calculator, it's probably right below your log button. You'll see an ln there. And what's cool about that is we can just use that ln button to or evaluate some of these if we need to. And it's just, instead of having to write out this entire log base e of x, we just simplify it to the natural log of x. So we're going to look at converting these from logarithmic forms or exponential into logarithmic, like we did with our normal logarithms. And then we're going to look at some properties, which the properties are all the same. And then we're going to look at some solving equations. So it shouldn't be too complicated, because the only thing that's really changing here is that we've got this little e, and then we've got our natural log, which is just ln. So if we want to convert this from exponential to logarithmic form, it's the same process as what we did in, it may have been 7.4, 7.5, but we're going to change what we have, like in the number 1 here. We're going to change this into a logarithmic form. So the way that we do that, if you remember, we'll have log base b, which our base here would be that little e. And it would be whatever this is equal to, that's what is being evaluated in our logarithm. So I'll have log base e of 24 is equal to x. And then we can just change this portion here. Since it's log with a base b, it will become the natural log 24 is equal to x. So that's all you've got to do in changing these from exponential form to logarithmic form. And it's not too complicated, to be honest. I'll just show you number 3 just because this x plus 5 in the exponent can throw people off. But if we want to change this to logarithmic form, we're going to have log base e, because that base here is going to become the base for a logarithm. So log base e of 72, because whatever we have our equation equal to in exponential form, that's what's being evaluated in our logarithm, and that's going to be equal to x plus 5. And then the only portion we've got to deal with here is changing log base e of 72 to natural log of 72 is equal to x plus 5. So these are pretty easy. All you've really got to do is remember that if you have a logarithm with a base e, you just rewrite it as the natural log, which is just ln. And we can also go in the opposite direction. So what I would suggest you do on these, if we're going to go from logarithmic to exponential, is just to remember that each of these, when we have an ln, a natural log, they have, you could write a little e there just to show that that e is actually your base. So when we write this in exponential form, that e becomes our base, and then whatever our logarithm's equal to, that becomes our exponent, and then whatever's being evaluated. So here we have natural log of x. That's what our exponential form equation will look like. So in number 4 from the notes, we would have e to the 58 power is equal to x, which you could actually probably plug that e to the 58 and figure that out. But I'll look at number 6 just to show you a problem with an exponent in there, or with the, not an exponent, a variable x minus 9. So if we want to rewrite this in exponential form, that e is our base. It's going to come down and become our base, and then 32 will become our exponent here. Whatever your logarithmic equation's equal to, that's what you use as your exponent. And then this x minus 9 is what everything's going to be equal to. So like I said, these are pretty easy to rewrite in different forms. I think the condensing and expanding for these are the exact same as when we just have normal logarithms. So the actual natural log doesn't change anything for you. So if we look at number 7, we've got natural log of 3 plus natural log of 16. If we want to condense this, we'll just condense it into one natural log. Since we have this plus sign here, that property tells us that we're multiplying 3 times 16. So we'd end up with natural log of 48. So there's not too much here. For those. All the properties for your logarithms are the exact same for your natural logs. And then when we look at expanding these, like I said, they're the exact same. So if we want to expand number 10, we've got this, we've got this natural log 5x. The easiest way to split this up would just be create 2 separate natural logs and just put a plus sign in the middle. So we'd have natural log 5 plus natural log x, which we're not going to focus too much on those. But all the properties that we've done for logarithms apply with natural logs, except they're just ln. That's the only difference. Everything else stays the same. So then when we look at solving these, we have the exact same process as when we were solving our logarithms that we just did in the last section. So when we have a natural log on each side, they both have a common base of e, and there's one single logarithm on each side, like on 13. All we've got to do is knock out those natural log signs, and then we'll just solve everything. So everything in parentheses we'll just bring out and set equal to each other. So 4x minus 27 equal to 15 minus 2x. And then let's see, we would solve for x, so we'd be left with, we'd add 2x. We get 6x. Then we would add 27, which this is just solving equations. That'd be what, 42? So an x would be equal to 7. And then we've just got to make sure we plug in our answers and check on which that would work. So just make sure that when you're doing this, we check for extraneous solutions. The only trick here, the only time these will get tricky for you, so the solving equations is just like what we just did in 7.7, except, or no, there's no exception. Everything's the exact same. And the only part that will give you some trouble is like on 14, we've got to condense this left side. So we would make, since we have this 2 multiplied in front, our properties of our logarithms tell us to make that 2 the exponent of k. So I'll just show you this again, which we've done this, but so once we've done that, now we can drop our natural log signs because we've got the single logarithm on both sides, and they have the same base, so everything's the same. So if we want to solve this, we'll end up with k squared is equal to 2k plus 15. So now you'll notice that this is the only time you'll run into some trouble is when you have like a k squared or like an x squared, because the way that we solve this is just not so obvious. But usually you're either going to factor or solve by square roots to solve that. So in this case, we would just move negative or 2k to the left, so it would be negative 2k, and then we would move 15 to the left, so it would be minus 15 equal to 0. And then we would factor that with k minus 5, k plus 7, and split those up, set each equal to 0. Set each factor equal to 0, and we'll get k is equal to 5, k is equal to negative 7. Which the only, actually, what am I talking about? We wouldn't use negative 5 and 7. We'd use negative 5 and 3. My bad. There we go. I was looking at my notes, and I was reading them totally wrong. Okay, so we would use negative 5 and 3. Then that would give us k is equal to 5, k is equal to negative 3. The only thing you've got to watch for is plugging in your answers to check for extraneous solutions. When we plugged in k is equal to negative 3, it would not work, but k is equal to 5 would work. But like I said, that's exactly the same. We're not doing anything different here than what we did in the last section, except we just have an ln, which means a natural log. So that's the only thing that changes here. So I think you probably won't have too much trouble with this. But we'll go over some examples in class and look at everything again. But this is just kind of your introduction to all this. I bet a lot of you will be able to use this and just complete all of your homework. But I'll tell you what questions from the homework you need to do, but that's it for this video.